Hi everybody, I'm Andy. I work on CUDA and CUDA-Python. I lead a product team at NVIDIA to help bring CUDA to the Python landscape. Today I want to talk about three things. How do you expose a GPU to something like Python? What are the different modalities that you might program it on? Like what are the things that are going to be affected, and how you have to think about the GPU when you're programming Python for it. Second, I want to talk a little bit about the evolution of hardware. Probably anybody in here computing on GPUs today? Okay, everybody has a laptop with a GPU probably, but the future of GPUs is changing quite a bit, and I want to kind of explain that to folks. Maybe you're not going to use it today, but if you start to take a job where you're going to start scaling on Blackwells and big clusters, you kind of show how we're thinking about that. And finally, like the future of a lot of the applications we're seeing is really multi-GPU, multi-node. I think I saw a talk earlier today where there's like, if you need to go to multi-node, good luck. Well, I'm here to tell you, we are thinking about it, and here's some ways we talk to people about it and help them work together. So let's start off with how you compute on a GPU. So if I take just a very crude view of a von Neumann computer, I have something that holds memory, my disk, or holds programs, my disk. I have something that computes my logic units, my CPU. And then over here, it's maybe not super clear, but this is supposed to be system memory. So I have something that's holding memory as I compute with my dictionaries, my arrays, and so forth. And then I have the GPU over on the right, your right. So in this world, if I want to do write a library that's accelerated, first thing I do, I load up the program, I load up the data, the CPU will put it in your system memory. The CPU will do some calculations, whether this is just filtering a data system or doing fast Fourier transforms or whatever it is, the CPU is doing some work. And then to use the GPU, you'll copy, and what ends up happening is the CPU says, hey, take something from my memory and copy it over to the GPU. It all has to go through the CPU typically. And then we get to CUDA, and the GPU does some work, and we copy back. The CPU doesn't work, we copy back. The GPU doesn't work, copy back, and eventually we're done, and we go back to I/O. Okay, so you can kind of see a lot of times I relate this to the CPU is something that can coordinate very well. It can do pretty much anything that you throw at it these days, but it's going to do it slower with fewer cores. And every once in a while, you need to do a lot of work all at once. And that's where the GPU comes in. If you're going to take a load of school children to the museum, you don't want to put them in individual cars. You want to put them in a big bus. And that's a very similar idea with CUDA. Now, how would you do this today in code? Well, let's start with NumPy. NumPy, I think most people know what it is, right? It's an array-based computing system. And there's a system called CuPy, developed by Preferred Networks, that gives you a very similar style of computing. It's pretty much a drop-in replacement for NumPy and SciPy. So in this case, maybe I have an array on the CPU. Let's just take a random array. I have maybe another array that I might be working with. I explicitly copy it, so NumPy creates the array, CuPy will then copy it to a GPU. So that's my copy step, right? And then I can do some calculation. So in this case, I'll do it on the GPU. So my AX plus Y is just what we call a Saxby, but I can do it. It's all on the GPU. You didn't have to worry about launching a CUDA kernel or thinking about the whole host of things that are running on the CUDA kernel. The CuPy does that for you. And then at the bottom, I might pull it over. I might say, give me that value. Now, of course, there's a lot of ways that people will use CuPy and things do this more implicitly, but this is the basic idea. The basic idea is I have some arrays, I copy them over, come back. Well, this is PyData, so we like pandas. Well, pandas gives us a lot of the same kind of features, except we don't always just think in arrays and integers or floats. We think in data structures and things like angles or degrees. And so the same idea, if I create a data frame, I'll use the popular library cuDF. If you have any questions, the guy in the red shirt over there who works on cuDF every day, wave Lawrence, thank you. And cuDF gives you the same exposure of the GPU as pandas gives you to the CPU, for example. And so in this case, you would think I'd have to move everything else, but no, I just call multiply. And it's under the hood doing just what CuPy did. It's moving the arrays over, setting up the computation, launching a kernel, and then coming back and giving you something you can print off to the screen. So this is a case where, well, this is a data science library that actually is focused on data science. So we don't have to teach you all about arrays and copying and things like that. So by using an exposure at the data array level, you kind of don't have to think about, oh, where is my data? But at the same time, I am using cuDF. It doesn't just come for free, for example, right? So, and cuDF participates with CuPy or NumPy, and like it figures out where arrays and things like that are. But you still have to know you're on a GPU. And then there come along like machine learning libraries. PyTorch is a very, very popular choice. And the same idea, I import Torch, I do a Saxby, but in this case, I usually give a Saxby a function, but it's the same idea as a CuPy version. But here I'm giving it this data object, the Torch tensor. The Torch tensor has a lot richer data structure underneath it that knows where it's at, what kind of device you're computing on, and it's got a framework approach. Like the framework knows all the details, and then I call out, I do my Saxby, and you notice there's nothing in here, like I install Torch, it could be on a CPU, it could be on a GPU, it could be distributed. You don't know anything about it, but this code works pretty much everywhere. So this is like what you might think of as a framework approach. So those are like three levels, right? Level of like an SDK, that like an array library, level of a domain library like pandas that knows about data science, and then the level of a framework like PyTorch that handles all the details for you. But there's one thing you noticed when I originally did the graph, I had a whole bunch of going back and forth, and really what I want is I want to just go from my I/O to my GPU and back very often. And this is where the frameworks, sometimes you have to tell them a little bit more about what's going on. And for example, if I use cuDF as opposed to CuPy, cuDF will know, hey, I just read this Parquet file, I read this CSV file. It'll use the direct path, which is called GPU direct storage, and pull out the right bits from your I/O system. And so sometimes it pays to know a little bit more about the system in order to get the highest performance. And to get this whole performance, the maximum performance, often you'll see people say, oh, we got 1,000x on CUDA. And really, you're usually not getting 1,000x just by doing the top level framework style. You're doing it by using the entire platform. And that's what makes CUDA a real platform, and why it continues to be the top GPU platform, software platform that you see on the market. And so like we covered, like there's frameworks, DSLs, and whatnot. But then prior to 2024, we really only had what I just showed you, PyTorch, cuDF, CuPy type array systems, and then we had host time, runtime tools. There's this big gulf between you can know data science or machine learning, or you have to know low-level hardware drivers. And we realized it's probably not how most people program, so we've been working to fill in these gaps. And the first kind of gap we look at is, all right, Python, like if you look at PyTorch today, it just takes your Python code, goes to C code, and then takes it to the GPU. So first thing we want to do is take the things that run on the device and actually make them so they're just Python. And so we have a whole stack to get that done, device libraries, kernel authoring libraries, and like interaction with the compiler stack. And the compiler world is evolving quite quickly to accommodate all the AI compilers. Well, we can tap into that for Python as well. So the next piece is communication libraries. And I'll go into depth in this in the latter part of my talk. So we expose communication libraries, and then we expose our accelerated libraries that are written by custom NVIDIANs who often work on a very specific thing and like to get just the right version of a GPU and all the various ways of optimizing that comes in these things. And so we're putting all this together in the CUDA-Python ecosystem, and here's a snapshot of all those different libraries, and I'm not going through every single one. The good news is they're interoperable. You can mix and match layers. You can learn how to use these pieces, but at every level, if I want to get more performance out of my system, I now have a full platform inside the Python language. Happy to say you can install all of this with Anaconda. Anacondans, I know Mo and Julian I see in the room. Go ask them how to get started. It ships right now with CUDA 12. I think Jack's somewhere and he's doing a Jupyter system as well with CUDA. And they can talk to you about how they've deployed this to their users. They're million organizations, 47 million plus users. And the good news is because we're using standards like the Array API and DLPack and things like that, it exposes itself to the entire PyData ecosystem, not just NumPy or not just pandas and so forth. Okay, and if you want to learn how to use all these tools, I think my colleague Katrina Reel, I don't know if she's in here, she's in the back. She gave a lightning talk this morning about the Accelerated Computing Hub. This is an open source resource for learning CUDA. We started with Python, now there's the C++ people saw that was so nice, they started putting their stuff into it, so we will allow C++ folks to come, but and in more languages in the future, we're not too picky about that, but this is a resource that's open source. You can clone it, run it, modify it, share it, report bugs, add your examples. We're very interested in working with the community to teach how all these different layers work. But let me give you a story about how one team we've been working with actually has been able to take something like this and make it work for them. This is the Frosty team, and they were part of the NASA Roman telescope rollout. And given the mission to help identify supernovae, and so as you might know, supernovae don't happen all the time, so you can't just observe them at any point in the sky. So you have to have some way of finding when they're going to occur and like match up with all the other telescopes that ever occurred. And it turns out to be a very large data problem. And so they started at NumPy because they knew NumPy, and a lot of folks like, yeah, start with the things you know. They moved to CuPy, and while they didn't get quite the performance they needed, they wanted to have those advanced libraries that I was talking about. And so nvmath-python became the big driver. And so nvmath-python is just a reimagining of our math libraries. We have over 80 math libraries, and often it's just like, I want to do a matrix multiply, but I have to know if I'm parallel, if I'm sparse, if I'm where the memory is, if I'm participating with multi GPUs. It just becomes a complexity of choices to get the maximum performance. So we came together and said, we really just want one interface to give everyone state-of-art performance, no matter where you are, works on CPUs, works on GPUs, and allows you to do things like FFTs here, where using things like Python context managers, we can do things like save on the FFT. So if folks ever did FFTs, you plan out how the computation happens, and then you do the execution. And this is very common in computational mathematics, where I have a lot of computation going on at once, and the caches will differ based upon the type of architecture I'm working with. And so we give you things like this, and there's a whole lot of libraries coming to this. We have dense linear algebra, we have FFTs, we're bringing sparse linear algebra this summer. And there's a talk, might not be super easy to see for everybody. I didn't realize how low the screen would be, but there's a talk on YouTube, and you can see like all the different ways they're bringing all of our math libraries to the Python user. And it's as simple as conda install nvmath. Now, if we go back to our use case, we're trying to detect supernovae, and you can see here we have tens of thousands of images that have to be denoised and matched and cross-examined. And so the way the team did this is they do pre-processing type calculations, they do an FFT, and they post-process it out. So they went from a CPU to a GPU, and they got that nice 23x kind of performance, something that you clean up your code, you vectorize it, you get it to a GPU, and you're expecting to see a pretty good performance if it has enough work in the problem. Your mileage may vary. If you're just searching through strings, sometimes that doesn't work quite as well. But then nvmath-python was able to take them with the optimized version of the library from our engineers and get an extra, 16x performance. And so this is a very typical pattern that we see of like, come use the community tools and then come use the expert tools. Okay, with that said, CUDA-Python's here. Check out the Accelerated Computing Hub. Meet the folks who are building that in the room. And we're going to be here all day, so definitely come find us. But, well, we're a hardware company. We're always thinking about the future of hardware. We're not thinking like, these are the things we did last year, so it's the things we're doing next year. And this kind of comes down is how is the hardware changing and how does Python get to take advantage of that? The newest architecture is called Blackwell, and this is a long line of architectures that have been available through CUDA since 2016 in this case. And you can see how every year there's more flops, better hardware and so forth, so your applications can get more perf for their buck. But there's no free lunch. You often have to change how your code works, and we look at how we can help the community take advantage of that. So in this case with Blackwell, some really interesting new things that probably folks here care about the most is that we have these next generation tensor cores, so all of our matrix multiply things get very fast, even faster. New streaming multiprocessors are going to have even more flops on them, so if you do have like a computational heavy load, you will get a little bit more flops if you're using the right methodologies and so forth. But the thing that really I look at is the memory. Our memory is going to 2x the memory bandwidth. So for data, that means that I can actually start computing problems maybe even faster than I can if I went through the CPU. I can just go straight to memory and so forth. Here's a case showing how our next generation of tensor cores are producing AI inference that's on the order of 6x faster just by using the next level card. And so a tensor, for those who haven't seen it, like a tensor core is a system that, like a streaming multiprocessor would just take and manage a thread, a tensor core manages tensors together and will present matrix multiply accumulate operators that then make it stream through the processor much faster. And so if you can get your code to use those things, it'll be, you'll get top performance on our cards. And in order to help the industry and the world to understand these things, we have an array of libraries, and I think Warp might be a very interesting one for this community, where we're taking physical simulations and using Python and other things to allow the simulation world and in this case, a lot of graphics. You can see the balls falling. But no matter what your industry, no matter what your problem, there's probably somebody who's been working on it in the CUDA ecosystem. And we recommend start out at one of the libraries, these domain libraries that we work with every day, and learn from that. And then as you hit more problems, you're going to end up coming back down to that stack and learn more of the things you need. So just to, this is another one of those charts that show all the various things that are changing, but just taking one thing of how you might think about how your code has to change. So my chip-to-chip interconnect is now going from 900 gigabytes to 10 terabytes. And so what that kind of means is this old model I was showing early, we need to shift it around a bit. We'll move memory to be the center of our workload and our CPU to be just another thing that does work for us. And we had already talked about shifting the data over, but just to highlight, like now our workload looks like load data from your I/O, work on that shared memory, because now it's much, much faster on the sort of Grace Blackwell machines that are being released today. And then your CPU is still working, it does the task it does best on. GPU isn't bottlenecked by going through the CPU. The only one little detail is you have to tell it to use that type of memory and so forth. And so working with library writers to make these things as easy as possible so that when you're using our libraries, you're getting this model of a computer as opposed to the one that was so famous 20 years ago, if you will. And of course, a GPU no longer looks like that little box I showed you. We at NVIDIA are building massive machines, and GPUs are growing to fill rooms with these NV72 with 72 GPUs in a rack. The Grace Blackwell knows what we're talking about, but also programmable switches and so on and so forth. So the whole ecosystem, the whole platform, if you're looking at like scaled users, this is kind of where the industry is going, is using all these things together in concert. Which takes me to our last round of our last topic, and I'm a little faster than I expected, but is multi-node, multi-GPU. So we talked about accelerated libraries, about how you can use Python and use the entire stack. We talked about how the architecture is changing, and you think about the multi-node, but also even in the single node, you think about how memory is going to interact with each other. So once you go to a single core, just like Python, if I go from a single core to multi-core, we saw the free threading talk earlier, there are different considerations that occur. Mainly, how do you distribute your data across these different nodes and then across the different GPUs? And why are we doing this? Like, the number one reason is just that data is exploding. I don't think I have to tell anybody here, but like, here's a study in 2023 that's showing how the data volumes are keep on growing no matter what we do. So maybe it's AI slop, but even still, like, our processors our businesses are wanting us to process more and more data. And so that journey, that original scientific team, like, they went for NumPy, works super well on a single, perhaps we have a DGX Spark box that fits on your desktop, to the workstation that has multiple nodes in it. And often CuPy you can kind of make CuPy work here. It's a little bit harder, but we do certainly have codes that do that. To the clusters. And when you work to a cluster, you have to make decisions. Just like if you want to do multiprocessing, you have to do multiprocessing, threading, subinterpreters, those sorts of things in Python. The two major decisions kind of made is, do I do explicit parallelism and use communication libraries like MPI, which does message passing, or SHMEM, which does shared memory models and so forth? Or do I do something implicit, like something like CuPy? Well, I'll introduce CuPy numeric, but a system like Spark, where you don't really have to know where your computation exists. You can describe your computation, and the system kind of maps it out for you. So there are advantage trade-offs here, right? And we can kind of characterize those a little bit in your typical, productivity versus speed, where I want to be fast to code, but I also want to be as fast to run. I want every bit of performance I can get. And so certainly explicit parallelism using MPI and shared memory will be much faster to run. You do have to understand a different programming model. You have to understand how your data works. You have to understand what layers of software is installed on the OS and so forth. And we have Nickel, which actually simplifies both these systems on a GPU. So you can go direct GPU. So if this talk was only about parallel computing, I would have shown how now you can get GPUs to talk directly to each other through Nickel and so forth. But so in my career, and lots of folks here, we've seen Dask and Spark kind of come up, and they're using more task-based systems. They take your code, they take the sequential operations, break them up into tasks, and then they determine the distribution based upon that task. So it's not as hard to understand as message passing. I don't have to understand exactly how many bytes are going to be processed. I don't have to understand like which hardware is where. But I do have to like explicitly say, like, this is my distributed array, this is my distributed set of tasks, and so forth. And then the system will map it out. And so more productive than MPI typically, but not. You're going to sacrifice some speed because now you have a scheduler and other systems to run in addition to your program. And then finally, we're seeing, just like before, we said, hey, you can use a framework like PyTorch. Well, now that we're seeing frameworks come and try to give you the same coding experience in a high-level interface. And so PyTorch and JAX both run on multi-node, multi-GPU systems. You have to configure them correctly, and sometimes they break because of bugs, but it's there. And then there's cuda-core, which has like things like Dask interface as well. But we're launching cuPyNumeric, which is built on top of the Legate system, which came out of Stanford on top of Legion and Realm. Very similar to Dask if anyone's ever worked in Dask before, but it's a different system that knows a little bit more about your system. And if you want to know more about any one of these types of computing, I definitely recommend checking out these various YouTube talks. They were all given at GTC, but now they're on YouTube. So if you just, that particular number plus the title there will get you directly to the talk. And they go through some of the trade-offs in each one of these systems. But let's just dive into cuPyNumeric a little bit. So we've been working with Dr. Nguyen at Stanford Linear Accelerator, and she works at trying to explore matter at atomic scales. She has similar to the first scientists we worked with who were using a telescope and generating data. She generates data through X-ray system where they excite a material with lasers. Out comes a nice matplotlib plot, and at the end of the day, she has 1.6 million plots that she has to go through here. And it's a big filtering problem. I don't know if you can see, but there's these little red squares, and she's really looking at the interactions of those red squares. So she has a program that has to sort through this data, find the interactions of the molecules, and then compute the interesting parts of the molecule, and like do this continuously. And they ran into a huge problem where as they go to their next laser, it's going to be not maybe just 1 terabyte, but hundreds of terabytes. And so they're just the typical, like we're moving from terabytes to petabytes of data. And you can no longer do that on a single computer. A single network can't, or a disk can't get it to you fast enough to compute. So this is where she wanted to move to a Perlmutter and a scaling system. cuPyNumeric is a system where we take exactly her code and use NumPy interface. And so we have a drop-in replacement for NumPy that has something like 70% of NumPy implemented, most of all of the array API if you're doing just standard array things. And your code looks pretty much the same way. And underneath the hood, we'll talk about a little bit later, but it's breaking it down into tasks and computing how it might be distributed on a cluster. So Dr. Nguyen's code went from something that took many days to compute to something that took very few minutes. She used to give me numbers, but they kept changing, so I took them out of the slide. But she's, they're working to now use cuPyNumeric as their next system as they're bringing up the next linear accelerator as it will bring so much more data. But then there's other things you can do as well. So we have a team that wrote XGBoost at NVIDIA, and most people I think here have done some classification with XGBoost. And so in the same way, we want to use the same arrays. And one of the things about XGBoost is there is a GPU version, but it is very complicated if you ever dive under the hood. So by giving an array system like cuPyNumeric, we're able to vastly simplify that code, and there's a few interesting things we've been able to do with that. So in this case, we have Legate Boost. You just use over cuPy, you might use cuPyNumeric, and over Legate XGBoost, you use XGBoost. And so the same code here, I'm generating my data however it comes in. In this case, I'll just use a random generator, and then I'll change my model definition a little bit. In this case, so it's not drop-in replacement, because in these cases, just even what arrays you use will change a little bit, but at the same time, it's a pretty close module, and then you just do your fit and predict, just like every other scikit-learn interface. So XGBoost has the feature that it does scale to over 1,000 GPUs. As far as I know, it's the largest XGBoost calculation with 8 terabytes of data. And now if this is random data, you got to load 8 terabytes, and that's an engineering problem. So we'll let the DevOps take care of that. But we are at this case, because we have these tools, we can create higher level libraries. Probably more interesting for this crowd is that not only because you have this large compute capability, you can do new interesting things, such as use it to pick which uncertainty model you're going to use. And so there's capabilities into it to like use normal distributions or quantile regression. And because you're in this parallel mode, you can actually do quite a bit as you start computing. And here's a little image of Rory, the main author, finding the right XGBoost iteration, because he's now on a GPU, he can go much faster, he can get a much tighter bound on his data using the different distributions. We also have it also provides things like batching, so that if you have an online learning scenario where I have more data coming in and it gets, for example, I think someone was talking about doing your guides, and you learn like as your model computes, you can actually add in more training. And here's a case where, yeah, I can batch through, and you can see the training error. If I did it all in one, you get the same error rates as I iterate if I did it in 10 batches. So you can imagine a system where I have a live XGBoost cluster going on, and I'm adding data to it, and it's still learning. It's something that's been very difficult on a single node scenario. We're also built out like mixed models. So theoretically, you should be able to get better performance in your model, whether you're using a kernel regression, the normal, very linear kind of correction term, and you can see at the top it's much cheaper, but it's not as accurate. Or I can switch down to trees, or I can actually combine them to get even better. So even doing an ensemble on the ensemble model itself. And because we have such a high level interface, this is something we would never be able to do in just XGBoost, because it was too difficult to like put these things together. And I asked Rory, I'm like, well, who in practice actually does this? He's like, well, all the papers say it should work, but nobody does it. So we'd love to hear from you if you want to try to use something that goes beyond the traditional XGBoost. All right, so that was XGBoost, and definitely check it out, especially if you have scaling problems like classifiers and you can't just move to PyTorch like I think the last folks did. So appreciate that a lot of folks will just switch to deep learning in some case to get these numbers, but I know a lot can't do that due to regulatory type things. But let's just talk a little bit about how the Legate runtime system works. I kind of alluded to this, but you have a bunch of calls. So I have cupa-numeric, which gives me my array system. And I might have some lib-foo, like in this case, XGBoost is intermixed in between these things. The libraries get converted into tasks just based upon the library is written in a way that's a task system and so forth. Legate runtime will schedule it out on the nodes and so forth. We also, underneath the hood with Legate, it has a unified data abstraction. And this data abstraction allows us to take Legate runtime and understand the difference between an ND array, a data frame, a pandas series, in this case, a sparse matrix. And by having that distribution and understanding how it was created, we get both the benefits of Arrow, which allow you to share memory from machine to machine, but also the benefits of scheduling these tasks directly on where the memory is at. And so that's what's fueling the advantage of cupa-numeric, and something that Legate gets us that you might not get elsewhere. Okay, so all that said, hopefully quick enough that we can have some questions, but 3 main points to catch everyone up. GPUs are catching up to Python. If you want to check out CUDA computing, come check out CUDA, the Accelerated Computing Hub, come talk to us. We'd love to port your applications over and see how to help you use CUDA. Hardware is moving to GPU-centric systems, so we definitely, as your organization looks at the next architectures, maybe you're thinking about this in 5 years or something, or 2 years, we will be much more GPU-centric, be able to load data, load memory, and work very fast from there. And then there's a lot of multi-node, multi-GPU stories emerging. I'd love to talk to you if you're working on something you think needs a multi-node system, and then kind of to learn what NVIDIA can do to help you. And since you stuck around, we give you a free gift, which is a free class on our deep learning platform. And so you can, all sorts of things to learn from NVIDIA. So yeah, just take a picture of the QR code and help my marketing people keep buying y'all beer. So thank you very much. That's all I have. I'm happy to take any questions.